The ocean has been hiding animals that every scientist on Earth agreed were extinct, some of them for hundreds of millions of years. They survived every mass extinction the planet has ever produced, and they are still out there tonight, swimming in the dark, completely unchanged. This is the story of 9 creatures that refuse to die, and what they know about survival that we don't. On a December morning in 1938, a young museum curator named Marjorie Courtney Latimer walked down to the docks in the port city of East London, South Africa, to inspect a fishing trawler's catch. She had an arrangement with the local fishermen. They would set aside anything unusual for her, and she would come down to look through the haul before it was sold or discarded. Most days, the catch held nothing remarkable. That morning, beneath a pile of sharks and rays on the deck of the trawler Nerine, she noticed a fin. It was blue, a vivid, iridescent steel blue, and it was attached to a fish unlike anything she had ever seen. The fish was about 5 feet long, heavy-bodied, with strange lobed fins that protruded from its body on fleshy limb-like stalks. Its scales were thick and armoured, its tail unlike any living fish she knew. Courtney Latimer had no idea what she was looking at, but she knew it was important, and she fought to have the specimen preserved against the objections of a taxi driver who did not want a 5-foot fish in his cab, and a taxidermist who initially refused to take it. She wrote to James Leonard Briley Smith, a chemistry professor and amateur ichthyologist at Rhodes University, enclosing a sketch of the fish. When Smith saw the drawing, he nearly collapsed. What Courtney Latimer had found was a coelacanth, a fish that science had declared extinct for 65 million years, a creature known only from fossils dating back to the age of the dinosaurs. The coelacanth had disappeared from the fossil record at the end of the Cretaceous period, the same mass extinction that killed the non-avian dinosaurs, the mosasaurs, the ammonites, and roughly 3/4 of all species on Earth. For 65 million years, no one had found a single trace of a living coelacanth. It was as settled a fact as any in paleontology. The coelacanth was gone. And then there it was, lying on the deck of a fishing trawler in the Indian Ocean, its blue scales still catching the South African sun. Smith named the species Latimeria chalumnae in honour of Courtney Latimer, and spent the next 14 years consumed by the search for a second specimen. The first fish had been poorly preserved. The taxidermist had discarded the soft tissues and internal organs, and Smith needed an intact specimen to study the coelacanth's anatomy properly. He distributed thousands of leaflets with illustrations of the fish across the ports and islands of the Western Indian Ocean, offering a reward for a second catch. It was not until 1952 that another coelacanth was landed, this time near the Comoro Islands between Mozambique and Madagascar. When Smith was brought to see it, he wept. He later wrote that he would not have been more surprised if he had seen a dinosaur walking down the street. The discovery electrified the scientific world. A second population was discovered decades later near Sulawesi in Indonesia, confirming that the coelacanth was not a single miraculous holdout, but a species that had been quietly persisting in the deep waters of the Indian Ocean for millions of years, unseen by science, unknown to anyone except the local fishermen who had been catching and discarding them for generations. The coelacanth is the most famous example of what biologists call a Lazarus taxon, an organism that disappears from the fossil record for a prolonged period, leading scientists to declare it extinct, only to be found alive. But the coelacanth is not alone. The ocean, it turns out, is full of survivors, creatures whose body plans date back hundreds of millions of years, who have outlasted every catastrophe the planet has produced, and who continue to drift, crawl, and swim through the modern sea as living records of deep time. Tonight, we are going to meet them one by one, starting with the oldest and working our way forward. Each one has a story. Each one is, in its own way, impossible. And each one raises the same unsettling question: what does it take to refuse to go extinct? If you're enjoying this content, please take a moment to subscribe. I'd also love to know if you were able to sleep any better last night than the night before. Let me know in the comments. And now, on to the next strange creature. If the coelacanth is the most famous living fossil in the ocean, the hagfish is the most overlooked and perhaps the most deserving of attention. Hagfishes are not beautiful. They are not charismatic. They resemble nothing so much as a pale, eyeless, elongated sausage, and their primary claim to fame in popular culture is their ability to produce truly extraordinary quantities of slime. A single hagfish, when stressed or threatened, can fill a bucket with thick, fibrous mucus in a matter of seconds. A defense mechanism so effective and so disgusting that almost no predator bothers to attack them twice. But beneath the slime and the unprepossessing exterior lies one of the oldest surviving vertebrate lineages on Earth. A creature whose ancestors were swimming in the Cambrian Ocean more than 500 million years ago, before the first fish had jaws, before the first plants had colonized the land, before anything resembling a modern animal existed outside the sea. Hagfishes occupy a strange and contested position on the vertebrate family tree. They have no jaws, they have no true vertebral column. Their spinal cord is supported by a simple notochord, the flexible rod of cartilage that all vertebrate embryos develop before their spines form, and that most vertebrates replace with bone as they mature. The hagfish never made that replacement. It kept the notochord, the way a building might keep its original scaffolding long after the rest of the structure has been redesigned around it. Hagfishes have no stomach. Food passes directly from the esophagus into the intestine. They have rudimentary eyes buried beneath the skin, capable of detecting light, but not of forming images. They breathe through their skin as well as through simple gill openings. They have 4 hearts, 1 primary heart and 3 accessory pumps that help circulate their blood, which, unlike the blood of most vertebrates, is isotonic with seawater. In almost every respect, the hagfish is a sketch of a vertebrate, a rough draft that evolution produced 500 million years ago and then, inexplicably, never revised. Their survival strategy is built on 2 pillars: slime and scavenging. The slime is remarkable stuff. It is not the thick, gooey substance that the word usually brings to mind. Hagfish slime is composed of long protein threads, some of them several inches in length, suspended in a mucus matrix. When the threads are released into seawater, they unfurl and expand, creating a gel that can clog the gills of any fish that tries to bite the hagfish. The volume is staggering. A single Atlantic hagfish can produce enough slime to fill several gallons of water with gel in under a second. Researchers studying the slime have found that the protein threads have a tensile strength comparable to nylon, and there has been serious scientific interest in developing synthetic hagfish slime for use as a sustainable alternative to petroleum-based polymers. The United States Navy has funded research into hagfish slime as a potential anti-shark material and as a clogging agent for defensive applications. As scavengers, hagfishes play an ecological role that is far more important than their reputation suggests. They are the cleanup crew of the deep sea floor, feeding on the carcasses of dead whales, fish, and other organisms that sink to the bottom. They locate their meals primarily through smell, using a keen chemical sense that compensates for their near blindness, and they feed by burrowing directly into the carcass, consuming it from the inside out. A whale fall, the body of a dead whale resting on the ocean floor, can sustain a community of hagfishes and other scavengers for years. And hagfishes are typically the first and most numerous arrivals at the feast. They tie themselves in knots to gain leverage while feeding, looping their flexible bodies into an overhand knot that slides along their length, pressing their mouth against the food and allowing them to tear off pieces of flesh. It is not an elegant strategy, but it has worked for 500 million years, across every mass extinction, every climate shift, every reorganization of the marine ecosystem that the planet has produced. The hagfish does not fight the future. It simply outlasts it, covered in slime, eating the dead, unchanged and unbothered in the dark. The Nautilus has been building the same shell for 500 million years. Not the same individual shell, of course, but the same design. A logarithmic spiral of chambers, each one sealed off from the last, each one filled with a carefully regulated mixture of gas and fluid that allows the animal to control its buoyancy with a precision that would impress a submarine engineer. The Nautilus adds a new chamber as it grows, moving its soft body forward into the newest and largest space, and sealing the old chamber behind it with a wall of nacre. A tube of living tissue called the siphuncle runs through every chamber, back to the very first one the animal built when it was a hatchling, and through this tube the Nautilus pumps fluid in and out, adjusting its buoyancy to rise or sink through the water column without expending energy on swimming. It is a system of such elegance that engineers have studied it for centuries, and it was old before the dinosaurs were born. The Nautilus belongs to the cephalopods, the same group that includes octopuses, squid, and cuttlefish, but it represents an ancient branch of the family that diverged from the others hundreds of millions of years ago. Its closest relatives are not the brilliant, soft-bodied cephalopods of the modern ocean, but the ammonites, the coiled, shelled creatures whose fossils are found in Mesozoic rocks around the world, and whose extinction at the end of the Cretaceous period, 66 million years ago, was so complete that not a single species survived. The Nautilus survived. It is the only externally shelled cephalopod left on Earth, the last living echo of a group that once dominated the oceans with thousands of species, from tiny coiled forms no larger than a coin to the great ammonites whose shells spanned 6 feet across. Everything else in that lineage is stone. The Nautilus is the one that kept breathing. How the Nautilus survived the extinction that killed the ammonites is one of the more compelling puzzles in paleontology. The asteroid impact 66 million years ago devastated the surface ocean. The phytoplankton that formed the base of the food web collapsed, and the cascade of starvation that followed wiped out virtually every marine animal that depended on the sunlit upper waters for food. The ammonites, which lived and fed in those upper waters, were obliterated. The nautilus, however, was a deeper water animal. It fed on detritus and carrion drifting down from above, and it could tolerate periods of scarcity that would starve a faster metabolizing animal. Its slow metabolism, its ability to retreat into its shell and wait, its preference for the deeper, colder waters where the effects of the impact were somewhat buffered. All of these traits, which in normal times might have seemed like disadvantages compared to the faster, more agile ammonites, became survival advantages in a world where the surface ocean had become a death trap. Today, the nautilus survives in a handful of species scattered across the tropical Western Pacific and Indian Oceans, living at depths between roughly 100 and 700 meters and rising towards shallower water at night to feed on the reef slopes. It navigates primarily by smell, possessing a simple pinhole eye, essentially a camera without a lens, that produces a blurry image far inferior to the sophisticated eyes of its octopus and squid cousins. It has not needed better eyes. It has not needed speed or ink or the ability to change colour. It has needed patience and a shell and a metabolism slow enough to ride out the worst the planet can deliver. The nautilus is not a fighter. It is a waiter. It waited out the Ordovician extinction, the Devonian extinction, the Permian extinction, the Triassic extinction, and the Cretaceous extinction. It is, at this moment, waiting out whatever we are doing to the ocean now, drifting in the dark water off the Philippines and Papua New Guinea, building the same spiral it has always built, adding one chamber at a time. Every year, roughly 500,000 horseshoe crabs are collected from the beaches of the Atlantic coast of the United States, transported to biomedical laboratories, strapped into steel racks, and bled. A needle is inserted into the tissue around the animal's heart, and approximately 30% of its pale blue blood is drawn off into sterile containers. The blood is not red. Horseshoe crab blood is blue because it uses copper-based hemocyanin to carry oxygen rather than the iron-based hemoglobin that colours the blood of mammals. But the colour is not what makes it valuable. What makes horseshoe crab blood one of the most precious fluids on Earth, worth roughly $60,000 per gallon on the biomedical market, is a substance in its blood cells called limulus amebocyte lysate, or LAL. LAL reacts to bacterial endotoxins, the toxic components of the cell walls of gram-negative bacteria, by forming a clot. This reaction is so exquisitely sensitive that it can detect endotoxins at concentrations of 1 part per trillion. There is no comparable test in all of medicine. Every injectable drug, every implantable medical device, every intravenous fluid bag used in hospitals anywhere in the world must be tested for endotoxin contamination before it can be approved for human use. The standard test for decades has been the LAL test, a test derived entirely from the blood of horseshoe crabs. Without it, modern pharmaceutical manufacturing as we know it would simply not function. A synthetic alternative called recombinant factor C has been developed and is gaining acceptance, but LAL remains the dominant standard. The horseshoe crab, in other words, is not merely a living fossil, it is a living medical instrument, and the debt that human medicine owes to this animal is staggering in both its scale and its invisibility to the general public. The horseshoe crab itself has been essentially unchanged for at least 450 million years. Despite its name, it is not a crab and is not closely related to crabs. Its nearest living relatives are spiders, scorpions, and ticks. It is an arachnid cousin, a marine chelicerate that branched off from the lineage leading to the terrestrial arachnids deep in the Paleozoic era. Its body plan is ancient and unmistakable. A broad, horseshoe-shaped carapace covering the front of the body, a hinged abdominal section armed with lateral spines, and a long, rigid tail spine called a telson that the animal uses to right itself when flipped over by waves. It has 10 eyes, including a pair of compound eyes on the sides of the carapace, and several simple eyes on the top and underside, including eyes sensitive to ultraviolet light. It has book gills, flat, leaf-like respiratory structures on the underside of the abdomen that function in a manner strikingly similar to the book lungs of spiders, suggesting a shared ancestral design. Every spring, during the high tides of May and June, horseshoe crabs emerge from the ocean along the Atlantic coast in enormous numbers to spawn on sandy beaches, with the largest concentrations occurring in Delaware Bay. The females crawl ashore, dig shallow nests in the sand, and deposit clusters of several thousand tiny green eggs, which the males fertilize externally. The eggs are a critical food source for migratory shorebirds, particularly the red knot, a long-distance migrant that times its northward spring migration to coincide precisely with horseshoe crab spawning, gorging on the energy-rich eggs to fuel the remaining leg of its journey from South America to the Arctic. The decline of horseshoe crab populations due to over-harvesting for bait and biomedical bleeding has been directly linked to the decline of red knot populations, creating a conservation entanglement that connects a 450 million year old marine arthropod to a migratory bird and to the global pharmaceutical industry in a web of dependency that no one anticipated and no one has fully resolved. There is something viscerally unsettling about the lamprey. It has no jaw. Where a jaw should be, there is instead a circular, sucker-like mouth, a disc of cartilage ringed with concentric rows of sharp, horn-like teeth surrounding a rasping tongue that the animal uses to bore through the skin and scales of other fish. The lamprey attaches itself to its host, locks on with its sucker, and feeds on blood and body fluids, sometimes for days or weeks, leaving behind a wound that often kills the host through blood loss or secondary infection. It is, by any measure, a parasite, and it looks the part. Elongated, eel-like, slimy, and eyeless in some species, with a face that belongs in a nightmare. Yet the lamprey is also one of the most scientifically important animals in the world, because it represents a lineage so ancient that it predates the evolution of the vertebrate jaw itself. Lampreys diverged from the lineage leading to jawed vertebrates more than 360 million years ago, and possibly much earlier. Fossil lampreys from the Devonian period are remarkably similar to modern species, suggesting that the basic body plan has remained stable for at least that long. They have no bones. Their skeleton is made entirely of cartilage. They have no paired fins. They have a single nostril on top of the head. they have a simple, two-chambered heart, and their immune system lacks the antibodies that jawed vertebrates use to fight infection, relying instead on an entirely separate adaptive immune system based on molecules called variable lymphocyte receptors, which were only discovered in the early 2000s and which represent an independent evolutionary solution to the problem of recognizing and fighting pathogens. The lamprey immune system is so different from our own that it has become a major focus of biomedical research, offering insights into how adaptive immunity can be built from fundamentally different molecular components. The lamprey's place in evolutionary history makes it invaluable to biologists studying the origin of the vertebrate body plan. Because the lamprey lineage diverged before jaws, paired fins, and true bone evolved, comparing lamprey anatomy and genetics with those of jawed vertebrates allows researchers to reconstruct which features were present in the last common ancestor and which evolved later. The lamprey genome, fully sequenced in 2013, has been instrumental in understanding how the genetic toolkit of vertebrates was assembled. Researchers have found that many of the genes involved in jaw development in jawed vertebrates are present in lampreys but are expressed differently, used to build different structures in different parts of the body, suggesting that the jaw did not require entirely new genes, but rather a reorganization of existing ones. In the modern world, lampreys are perhaps best known for their role as an invasive ecological disaster in the Great Lakes of North America. Sea lampreys, native to the Atlantic Ocean, gained access to the upper Great Lakes through shipping canals in the early 20th century, and in the absence of natural predators, their populations exploded. They devastated the native fish populations. Lake trout, whitefish, and other commercially important species were driven to near extinction in some lakes by lamprey predation. The control program that followed, beginning in the 1950s and continuing to this day, is one of the longest-running and most expensive invasive species management efforts in history, relying on a chemical called TFM that selectively kills lamprey larvae in their stream nurseries without significantly harming other fish. The irony is considerable. An animal that has survived for over 360 million years, outlasting every natural catastrophe the planet has produced, was nearly brought to ruin not by an asteroid or an ice age, but by a canal, and then was fought to a standstill not by a predator, but by a pesticide. The lamprey does not care about irony. It has no jaw, no bone, no antibodies, and no concern for the aesthetic preferences of the species that studies it. It has persisted since before the first tree grew on land, and there is no particular reason to believe it will stop now. In the shallow, temporary pools that form after heavy rains across every continent except Antarctica, a creature hatches that has been hatching in pools like these for 300 million years. Triops, the tadpole shrimp, looks less like a shrimp than like a small, flattened horseshoe crab, with a broad shield-shaped carapace, a segmented tail, and dozens of leaf-like legs that beat in coordinated waves beneath its body. It grows fast, absurdly fast, reaching adulthood and reproductive maturity in as little as 2 weeks, and it needs to, because the pools it inhabits are ephemeral. They fill with rain, they persist for weeks or months, and then they dry up and disappear. Every generation of triops is a race against evaporation, and the species has been winning that race since the Carboniferous period, since before the first dinosaur, since before the first mammal, since before the supercontinent Pangaea had finished assembling itself. Triops is frequently cited as the oldest unchanged animal genus on Earth, and while that claim involves some taxonomic nuance, the fossil species assigned to Triops may or may not be congeneric with the living ones, depending on which morphological features you prioritize. The basic body plan is unarguably ancient. Fossils from the Carboniferous and Permian periods, more than 250 million years old, are so similar to living Triops that a non-specialist would struggle to distinguish them from modern specimens. The compound eyes, the carapace shape, the segmentation of the tail, the arrangement of the limbs, all are essentially identical. Whatever selection pressures have been acting on Triops for the last 300 million years, they have not been pushing the animal to change. They have been pushing it to stay exactly the same. The secret to this extraordinary conservatism lies in the animal's life cycle. Triops does not need a permanent body of water. It does not need a river, a lake, or an ocean. It needs a puddle, and it needs that puddle for only a few weeks. The female Triops produces eggs, technically cysts, that are encased in a tough, drought-resistant shell capable of surviving complete desiccation for years, possibly decades, and potentially much longer. The cysts can withstand freezing, extreme heat, and UV radiation. They can be carried by wind across enormous distances, deposited in soil, and remain dormant until the next rain fills the depression they happen to be sitting in. When water arrives, the cysts hatch within hours, and the race begins again. This strategy, producing durable dispersible resting stages that decouple the organism's survival from the persistence of any particular habitat, is an extraordinarily effective hedge against environmental change. It does not matter if the climate shifts, if the local geography changes, if the pool that sustained the last generation never forms again. The cysts are everywhere, waiting in the soil, and sooner or later, somewhere, it will rain. This is why Triops has survived every extinction event in the last 300 million years. It does not need the ocean. It does not need the reef, the deep sea, the continental shelf, or any of the other marine environments that have been repeatedly devastated by mass extinctions. It needs dirt and rain. The Permian extinction, which killed roughly 90% of all marine species and 70% of terrestrial vertebrates, would have been largely irrelevant to an animal whose survival depends on temporary freshwater pools and whose eggs can wait out decades of drought in a state of suspended animation. The same is true of the end Cretaceous extinction, the end Triassic extinction, and every other catastrophe in the geological record. Triops simply waited, dormant in the soil, while the world above burned, froze, acidified, and reorganized itself. When the rain returned, Triops returned with it, hatching in the same puddles, building the same body, racing the same clock it has been racing since before the coal swamps of the Carboniferous gave way to the deserts of the Permian. It is the ultimate expression of a survival strategy based not on strength or speed or intelligence, but on patience and eggs that refuse to die. The deep ocean is a museum that never closes and never updates its collection. Its cold, dark, pressure-crushed waters have a way of preserving lineages that went extinct everywhere else, sheltering ancient body plans in an environment so stable and so removed from the turbulence of the surface world that evolution slows to a crawl. Two of the most striking residents of this museum are the chimeras and the frilled shark, animals separated by hundreds of millions of years of evolutionary history, but united by their refusal to change and by the deep, dark water that has kept them hidden from human eyes until remarkably recently. The chimeras, commonly called ghost sharks or ratfish, though they are neither ghosts nor rats nor true sharks, are among the oldest living lineages of jawed vertebrates. They diverged from the sharks and rays roughly 400 million years ago in the Devonian period and have been following their own quiet evolutionary path ever since. There are roughly 50 known species, most of them living at depths between 200 and 2,000 meters, and they are strange-looking animals by any standard. Large heads, enormous reflective eyes adapted to near-total darkness, smooth, scaleless skin, and a single gill opening on each side of the head, covered by a fleshy flap called an operculum, a feature that true sharks lost long ago. Their teeth are not the replaceable serrated blades of a shark, but fused dental plates that they use to crush the shells of mollusks and crustaceans. Males possess a retractable club-like structure on the forehead called a tenaculum, which is used during mating and which has no equivalent in any other group of living fish. They are, in short, deeply weird, and they have been deeply weird for 400 million years. The frilled shark, Chlamydocelicus anguineus, is a different kind of relic. Its lineage dates back at least 80 million years, and some researchers have argued that its ancestry may extend considerably further into the late Paleozoic. It looks nothing like a modern shark. Its body is long and eel-like, reaching lengths of 2 meters, with a flattened head, a terminal mouth positioned at the front of the snout rather than underneath it, and 6 pairs of gill slits, the first of which extends across the throat like a frill, giving the animal its name. Its teeth are trident-shaped, with 3 slender cusps arranged in rows that have been compared to the tines of a pitchfork, and they number roughly 300 in 25 rows. The frilled shark swims with a sinuous serpentine motion entirely unlike the stiff-bodied cruising of most modern sharks, and it inhabits the deep waters of the continental slopes and submarine canyons, typically between 500 and 1,000 meters, though it has been recorded as deep as 1,500. Both the chimera and the frilled shark owe their survival to the same basic fact. The deep ocean does not change the way the surface does. It does not freeze during ice ages. It does not boil during volcanic eruptions. It does not lose its oxygen during the kinds of anoxic events that have repeatedly devastated shallow marine environments. The temperature at 1,000 meters has been roughly the same, cold, just above freezing, for tens of millions of years. The pressure is crushing, the food supply is sparse, and the darkness is total. But these conditions, harsh as they are consistent, and consistency over geological time is the rarest and most valuable commodity on Earth. Animals that find a niche in the deep ocean and adapt to its conditions are insulated from the catastrophes that periodically wipe the slate clean in the shallows above. They are not invulnerable, nothing is, but they are buffered, sheltered, tucked away in the most stable environment the planet has to offer. running on slow metabolisms in cold water, waiting out the storms that rage above them. In the dark water off the coast of Japan, at depths where the last traces of sunlight have long since been absorbed, a shape moves through the water that looks like nothing evolution should have produced. Its snout is long, flat, and blade-like, projecting forward from the head like the prow of a ship. Its skin is translucent and pinkish, the blood vessels visible beneath, giving it a raw, unfinished appearance. Its eyes are small and round, and its jaw, the feature that earns the goblin shark its name and its reputation, is a mechanism of such startling violence that it seems to belong to a different animal entirely. When the goblin shark detects prey, its jaw does not simply open, it launches forward, catapulting out from beneath the snout on a set of elastic ligaments, extending several inches beyond the shark's profile in a fraction of a second, snatching the prey and retracting. The entire strike takes less than 1/10 of a second. It is the fastest jaw protrusion of any known shark, and it transforms the animal's face from something vaguely alien into something genuinely monstrous. A transition so dramatic that early photographs of goblin sharks with their jaws extended were sometimes mistaken for deformed or diseased specimens. The goblin shark, Mitsukurina austoni, is the last surviving member of the family Mitsukurinidae, a lineage that dates back roughly 125 million years to the early Cretaceous period. Its relatives swam alongside ichthyosaurs, plesiosaurs, and the great marine reptiles that dominated the Mesozoic seas. Those relatives are all gone. Every other member of the family is known only from fossils, and the goblin shark persists as the sole representative of a once diverse group, a single thread connecting the modern ocean to the world of the Cretaceous. It is found in deep water throughout the world's oceans, typically between 200 and 1,300 meters, though specimens have been recorded much deeper. It is rarely encountered, rarely studied, and almost everything we know about its behavior comes from the handful of specimens that have been captured alive or observed from submersibles. The launching jaw is an adaptation to deep-sea hunting, where prey is scarce and encounters are unpredictable. A shark that can strike from a greater distance with greater speed has a significant advantage in an environment where missing a meal might mean waiting days or weeks for the next opportunity. The mechanism works through a system of highly modified jaw ligaments that are stretched taut when the jaw is retracted, storing elastic energy like a drawn bowstring. When the shark opens its mouth, the ligaments release their stored energy, driving the jaw forward with explosive speed. The teeth, long, thin, and nail-like in the front, flatter and more robust in the back, are designed for grasping rather than cutting, suited to catching the soft-bodied squid and mid-water fish that make up most of the goblin shark's diet. The snout itself, the elongated blade that gives the shark its otherworldly profile, is packed with electroreceptive organs called ampullae of Lorenzini, which detect the faint electrical fields generated by the muscle contractions of nearby prey. The goblin shark hunts in total darkness, guided not by sight but by electrical sense, and strikes with a jaw that has been engineered by 125 million years of deep-sea selection pressure into one of the most efficient ambush weapons in the ocean. Despite its formidable reputation, the goblin shark is not large by shark standards. Most specimens are between 3 and 4 meters long, and it poses no threat to humans. It is a sluggish, slow-swimming animal with a soft, flabby body that suggests a low-energy lifestyle, cruising through the deep water with minimal effort and conserving energy between meals. Its rarity and its deep water habitat mean that it was entirely unknown to Western science until 1898, when a specimen was captured in Sagami Bay, Japan, and described by the American ichthyologist David Starr Jordan. Japanese fishermen had long been aware of the animal, calling it tenguzame, the goblin shark, after the tengu, a long-nosed supernatural creature from Japanese folklore. The name stuck, and it fits. The goblin shark is a creature of folklore made real, a face from the deep past wearing the body of an ambush predator, the last of a family that has been dwindling since the Cretaceous, still hunting in the dark, still launching its jaw at anything that generates an electrical flicker in the black water. We end where we began, in the deep ocean, in the dark, with an animal that should not still exist. The vampire squid, Vampiroteuthis infinalis, has a name that translates to vampire squid from hell, which is one of the most spectacular misnamings in the history of zoology. It is not a vampire. It does not drink blood. It is not from hell. It is, in fact, one of the gentlest animals in the deep sea. A small, soft-bodied creature, rarely exceeding 30 centimeters in length, that drifts through the oxygen minimum zones of the deep ocean at depths between 600 and 1,200 meters, feeding on marine snow, the slow rain of dead organic matter that sinks from the surface. It catches this debris using 2 long, retractable filaments that are covered in sticky cells, reeling them in like fishing lines and transferring the collected particles to its mouth. It is a filter feeder, a garbage collector, a quiet custodian of the deep-sea water column. And it is the sole surviving member of its entire order. The order Vampiromorphida was once more diverse. Fossil vampiromorphs are known from the Jurassic and Cretaceous periods, and they appear to have been more widespread and more varied than the single species that survives today. But the rest of the order is gone, extinct, erased from the ocean by the same forces that have pruned so many other deep-sea lineages over geological time. Vampiroteuthis persists as the last representative, a living relic occupying an ecological niche, the oxygen minimum zone, that few other animals can tolerate. The oxygen levels in its preferred habitat are so low that most fish and cephalopods cannot survive there. The vampire squid has adapted to these conditions through an exceptionally low metabolic rate, efficient oxygen-extracting gills, and blood that contains a form of hemocyanin with an unusually high affinity for oxygen, allowing it to pull usable oxygen from water that would suffocate most other cephalopods. Its appearance, despite the fearsome name, is almost endearing. Its body is a deep reddish-brown or purplish-black, with enormous blue eyes, proportionally the largest eyes of any animal on Earth relative to body size, that give it a perpetually startled expression. Its 8 arms are connected by a web of skin that it can draw over its body like a cloak, inverting itself to display the non-bioluminescent undersides of the webbing and the fleshy spines called cirri that line the inner surface of the arms. This defensive posture, called the pineapple pose by researchers, makes the animal look like a spiky dark ball, unappetizing and confusing to predators. When more seriously threatened, the vampire squid ejects clouds of bioluminescent mucus from the tips of its arms, producing a glowing blue smokescreen that disorients predators while the animal jets away into the darkness. Unlike the ink of shallow water squid, which works by obscuring the predator's vision in a cloud of pigment, the vampire squid's defense works by adding light to a world of darkness, a flash and a cloud where there should be nothing, buying time for an animal too slow and too fragile to outrun anything. The vampire squid is a fitting end to our journey through the ocean's living fossils, because it embodies the paradox at the heart of all of them. It is not fast, it is not strong, it is not aggressive. It does not have the crushing jaws of the goblin shark, the defensive slime of the hagfish, or the durable eggs of Triops. What it has is a willingness to live where nothing else wants to live, to eat what nothing else wants to eat, and to do both so efficiently that the margins of survival, thin as they are, have been enough to sustain a single species through millions of years of change. Every animal we have met tonight shares some version of this quality. The hagfish eats the dead. The nautilus waits in its shell. The horseshoe crab gives its blood. The lamprey attaches and holds on. Triops hatches in a puddle and races the sun. The ghost shark hides in the deep. The goblin shark launches its jaw at electrical shadows. And the vampire squid drifts through water too thin for anything else to breathe, catching falling snow in the dark. None of them are the strongest, the fastest, or the smartest. They are simply the ones that found a way to keep going when everything around them stopped. 500 million years is a long time to survive. It is long enough for continents to collide and break apart and collide again. Long enough for the atmosphere to be remade, for oceans to open and close, for ice to advance and retreat across the poles a dozen times over. Long enough for 5 mass extinctions to sweep through the living world and erase the majority of species each time. The animals we met tonight lived through all of it, not by being extraordinary, but by being adequate in the right way at the right time, in the right place, with the right metabolism, the right eggs, the right slime, or the right willingness to eat what no one else would touch. They are still here. The hagfish is still tying itself in knots on the ocean floor. The nautilus is still building its spiral. The horseshoe crab is still crawling onto the beaches of Delaware Bay every spring. The coelacanth is still drifting in the deep water off the Comoros, 65 million years after science said it was gone. They do not know they are relics. They do not know they are ancient. They only know what they have always known: how to find food, how to avoid being eaten, and how to keep going, one day at a time, in an ocean that has changed around them so many times that the only constant left is the fact that they are still in it. Sleep well tonight. The survivors will still be here when you wake. Thank you for watching.